Dr. M.A. Bhagyaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagyaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad-hoc networks, wireless sensor networks and wireless communication. She has completed 2 projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got 2 Best Research Paper Awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of 2 books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
Welcome to the UGC lecture series. In this episode, we are going to see about the AM modulation lab experiment, how we are going to set up the experiment and measure the values in a lab. The content of this flow is we are going to see the basics of amplitude modulation in the lab, what is the aim of this experiment, the apparatus required for doing this experiment, the theory, circuit diagram. There are various types of amplitude modulations like double sideband with carrier. This is popularly called as amplitude modulated signal. Double sideband suppressed carrier, this is also same as amplitude modulation, but without the carrier. Single sideband modulation, only one half of the sideband will be transmitted in single sideband modulation. Then we have vestigial sideband modulation. This modulation is same as single sideband, but a part of the upper sideband will be added up and that will be called as a vestigial sideband. This is a modulation of single sideband. To ease the generation and reception of the signal, we go in for vestigial sideband modulation. So, out of these versions of AM modulation, what we are going to see in the lab is double sideband with carrier, popularly called as amplitude modulated signal generation. The aim of this experiment is we are going to perform in this lab, we will learn how to perform the amplitude modulation and demodulation and to calculate the modulation index for various modulating voltages. So, the aim itself should say what we are going to do and what results we are expecting of it. So, aim is nothing but what is your objective. So, how about you are going to go into the experiment and do that will be taken as the procedures, but at the aim itself should say what you are going to implement and what you are calculating. So, for this amplitude modulation and demodulation, the aim will be learning to perform amplitude modulation and demodulation and what parameters we are going to measure, like we are going to calculate the modulation index for various modulating voltages. So, this is my aim of this experiment. So, what are all the components required? So, before starting up we should do some preparations. So, if everything is prepared, then we can go about constructing the experiment and taking out the result. So, for that we need to know what are all the components required. So, to do this AM modulation and demodulation, we will be in need of a transistor which is named as BC108, a resistors, capacitors, frequency generators, then CROs, cathode ray oscilloscopes. These are all for modulation purpose. For demodulation, we will be in need of a diode OA79, the multimeters or regulated power supplies, breadboard and connecting wires. With this, we will start up the experiment. First, what is required is before going into the experiments, you need to do some preparation. That is, before coming to the lab, you need to prepare yourself in the sense the knowledge that the theoretical part of it should be learned by you previously and you should prepare what you are going to do before entering to the lab. So, that is called as preparation. So, do the complete revision of AM modulation and demodulation, like if you are going to look into the previous lectures. In the first lecture, I would have given you details about what is AM modulation, what is demodulation, how the circuit works, etc. So, if you go through all those things, that will be your revision part. So, if you have understood the theoretical part of it, then we can go ahead with doing the experimental part of it. Okay. So, try to learn, revise what is AM modulation and demodulation, and also mathematically you try to calculate for example what will be the modulation index for. If we take up, if the modulation voltage is 6 volts and Vm is 60 millivolts, Fc is 500 kilohertz, Fm equal to 1 kilohertz, what will be the modulation index mu? So, with this small amount of preparation, then you have to write a part of theory in the lab process. In that theory, you have to give certain idea about what is modulation, what is AM modulation, that is about the theory. So, typically in theory you can just say what is a modulation. Modulation is defined as the process by which the characteristics of the carrier signal is varied in accordance with the modulating signal. The baseband signal is referred to as the modulating signal and the output of the modulation process is called as modulated signal. Amplitude modulation is defined as the process in which the amplitude of the carrier wave is varied about the amplitude about the baseband signal. So, a small part of theory which will introduce what is modulation, what is AM modulation, etc. So, after the theory, continuing the theory where we have just defined what is your AM modulation, we just continue with the envelope of the modulating wave has the same shape as the baseband signal, provided it is going to satisfy two requirements. The first requirement is the carrier frequency must be much greater than the highest frequency component of the message signal. So, you are going to select two signals, one as the message, other as the carrier. So, the first constraint is you need to select the carrier signal which is having the highest frequency component very much greater than, you can see this greater than symbol, it should be very much greater than the message signal's maximum frequency, message signal maximum frequency. Okay. This is one of the constraint. Second constraint is the modulation index must be less than unity. So, by experiment we can also verify what will happen if the modulation index is greater than unity. So, modulation index should be less than unity means the voltage that you are going to set for the message with respect to the voltage of the carrier, that is going to define the modulation index. If modulation index is greater than unity, you cannot exactly see a AM modulated waveform. So, when these two constraints are met, you will get an amplitude modulated waveform. So, there is a circuit diagram bring up for the AM modulated waveform. So, this is a circuit diagram for amplitude modulation, where you will be using the transistor BC107. BC107 is a transistor. In that transistor, you can see there are three legs. One will be the emitter, the base and the collector. So, as a component you can view the BC107 as like this. This is the component top view of the transistor, where there will be a small notch, the leg which is very close to this notch will be the emitter, followed by the base and then the collector. So, this is a top view of BC107. Then you can take this transistor and insert it into the breadboard, where you can segregate the three legs, one as the base, the other as the collector and other as the emitter. Then after segregating you need to insert resistors. So, altogether we are going to use 4 resistors. These resistors are nothing but for biasing the transistor as well as providing the input message signal and this is your carrier signal and your message signal. So, you need to collect the RC value, which is about 10 K, which will be connected between the collector of the transistor to the power supply, which is about 30 volts. Then resistor R1 and R2, R1 is about 20 K, R2 is about 10 K. This is for this setup is called as voltage divider biasing. This is done to bias the transistor in order that it will fruitfully respond the carrier signal which is provided to the base of the transistor. So, R1 is 20 K, R2 is 10 K. Then you have a emitter resistance Re, which is also about 10 kilo ohms. So, to the emitter resistance you need to connect a function generator. This function generator will operate as a message signal function generator. So, for this message signal function generator, you should have a frequency less than the carrier signal value. So, you can set this approximately to be equal to 1 kilohertz and the voltage of this signal to be nearly 60 millivolts. There will be a bypass capacitor CE which is going to pass away all the AC components to the ground. So, this signal will be passed into the emitter of the transistor. To the base of the transistor, you connect C in, this is a blocking capacitor which blocks all the DC values, and this will be your another function generator. The signal that is provided in this function generator will act as a carrier signal. So, in this carrier signal, this carrier voltage should be much greater than the message voltage, in order that the modulation index will be always less than 1. Okay. So, for that you can have this in some volts. This can be in voltage range, this can be in millivolts range. So, and also the frequency should be more than hundreds. The relation between the frequency of the carrier and the message should be, FC should be at least 100 times FM. So, like that, for a small example we can have this to be 6 volts and this to be 500 kilohertz. Then this is the, now we have completed all this part, right, and the output AM modulated waveform will be available over the collector of the transistor, which is taken as output through a coupling capacitor CC followed by the load resistor RL. So, the output across the RL will be viewed using the CRO. At this point you need to connect your CRO. Here we will be viewing the output, that is your modulated waveform. So, that is about the circuit diagram. Once the connection is over, after setting up the values of these voltages, we can go ahead with doing the experiment. So, as we have seen how to generate the AM modulation using normal breadboard, where you use the transistor as a nonlinear device. There are two resistors and R1 and R2 to bias the transistor. Through RE we provided the message signal, and through the base we provided the carrier signal. At the collector we got the output of the modulated signal, what we saw ringed up over the breadboard. In order to have more comfortable learning over the communication part, we can generate the same thing using kits. These are commercially available at many places. This is one such kit where we not be troubleshooting with respect to electronics, we can directly go with the parts learning with communication. We have a AM modulator part here and AM demodulator block here. To the AM modulator part, we will be providing the message signal whose amplitude can be adjusted using this knob, and the carrier signal, this amplitude can be adjusted using this knob. So, these are the test points. From the test points, we can just insert the probe from the carrier. So, this is the message where it will be passed on to the input. This is the carrier, this is the message. Once these two inputs are provided to the AM modulator, we can take the output from the output of the modulator block. So, that you can see using this DSO. This is the AM modulated output which is got from the output of the modulator block. The amplitude of the carrier signal is modified with respect to the amplitude of the message. So, your message signal frequency is here and the amplitude is here, and these are the carrier frequencies. So, this is your AM modulated output. So, when you look at the output, that is using your CRO, the waveform will be, what you get as a waveform will be looking like this, where the output produced will be the carrier waves. The amplitude of the carrier waves will change with respect to the amplitude of the message that is being provided. This is the amplitude of the message. Okay. The amplitude of the carrier wave is going to change. So, this is your AM modulated output. So, once you got this as output, you can get this by just adjusting the CRO's the voltage viewing level as well as the time scale. So, as you adjust the time scales and the level of voltages, you can get a smooth waveform. This just look like your AM modulated waveform. So, after getting this as the output, you have to draw this waveform. Once you draw this, then you need to capture or observe certain values. These values are nothing but what is the maximum output voltage, that is the maximum voltage of the modulated waveform. This value will be called as A max. This value will be called as A max. So, this you should not measure from this end, from here to here, right. You should measure only from the center line, right. This is your center line T. From here to here will be your A max. So, you will be measuring from this point to this point as A max. After measuring this point, then you measure A min. A min will be nothing but the minimum-most value what your modulated waveform is going to have. Once again, this should not be measured from here to here. You should only measure this part of it. This will be the A min. So, once you measure A max and A min, then we can calculate modulation index mu. So, the relation between A max, A min and mu is given by this formula. A max by A min will be equal to amplitude of the carrier into 1 plus modulation index divided by amplitude of the carrier into 1 minus modulation index. Therefore, solving this, we can get the formula for modulation index mu to be equal to A max minus A min divided by A max plus A min. So, we are going to just whatever we have measured, we are going to just substitute into this and then get what is the modulation index of our viewed signal. So, the design procedure, we have VC, that is a carrier voltage set to 6 volts, carrier frequency set to 500 kilohertz, message frequency set to 1 kilohertz, message voltage set to 60 millivolts. So, out of setting up all these things, when you are going to see the modulated waveform, we will be measuring A max. If the measured value of A max is about 1.6 volts and A min is about 0.7 volts, the modulation index is mu is calculated as A max minus A min divided by A max plus A min. So, A max is nothing but 1.6 minus 0.7 divided by 1.6 plus 0.7. So, you will get 0.9 divided by 2.3. 0.9 divided by 2.3, when you compute, its value will be equal to 0.3913. So, modulation is always a parameter, it is a unitless parameter, usually measured as or in terms of percentage it will be expressed. So, 0.3913 into 100 will be the modulation index in percentage. So, the value will be 39.13 percentage. So, for this typical values of measurements, we get a modulation index mu to be equal to 39.13. Once again, you can adjust A max, you can adjust your Vm voltage to some other value and then compute what is A max, what is A min. Like for example, this is first level experiment, first iteration is over, you can plot it as a table. You can plot it as a table. In the tabular column, we will be having like you can repeat it for serial number, what is the A max value, what is your A min value and what is the modulation index in percentage. So, first serial number you got your A max 0.6, A min 0.7, what is your mu you have computed 39.13 percentage. Then you can adjust your V min, once again take down the readings, what is A max and what is A min. So, in the lab we have done this experiment. While doing that, we got A max value to be equal to 1.32 volts, A min to be equal to 0.32 volts. So, for 1.32 and 0.32, what is your modulation index? You can do the similar way calculation like 1.32, this is for first, this is for second reading whatever you have noted down, 1.32 minus 0.32 divided by 1.32 plus 0.32. So, you get 1 over 1.64. So, when you do this, you get approximately 0.609. So, which will be in percentage, it is 60.9 percentage. So, your modulation index is 60.9 percentage. We will be calculating the modulation index for the modulated waveform whatever we have got. We have to measure the maximum, that is your A max, and the minimum value. From the A max and A min, we use a formula that we have shown in the PPTs, like A max minus A min divided by A max plus A min to be equal to the modulation index mu. So, for this particular waveform, A max value you have to measure the difference as the height of this modulated waveform starting from the baseline till the height. So, when you place the cursor at the highest most value whatever you have got, you get the max del y to be equal to 1.36 volts, the message signal minimum value, right. So, from here you can see the del y value is 320 millivolts, 320 millivolts. Now, you can compute the A max value, that is 1.32 volts minus 320 millivolts divided by 1.32 volts plus 320 millivolts. So, that will be your modulation index mu. So, like this you can take down some 5 readings. You can take down 5 readings and do the observation. In summary, we have just seen what is the aim of this experiment, then what are all the components required to do this experiment, then what is the operation of the circuit for the AM modulation. So, few questions you may try out and see in your lab. Find out the frequency occupied by the AM and FM radio broadcast station. So, AM is a very popular technique where the radio signals have been broadcasted. FM is also another very popular modulation technique where the FM radio is broadcasted. Now, just try to find out what are all the frequencies occupied by AM radio station and FM radio station. Second, this is a very general question. Second question will be, what will happen if the modulation index is greater than 100%? That also I have just told, but anyway you can see in the lab and find out that the carrier is going to go phase reversal. Thank you.